Okay, question 3 now. Question 3 is the Young's modulus question. So we've got some graphs here. You should recognise these all instantly. A is glass, B is steel, C is copper, and D is some sort of elastic material. You should just know those. If you don't, you need to learn them. Tensile stress. So two definitions. We need to define stress and strain. So tensile stress is F divided by A. So it is the tension force divided by the cross-sectional area. And tensile strain, that's delta L over L. So that's the change in length, which will be an increase because it's in tension, divided by the original length. Okay, they are referred to on your formula sheet here, tensile stress, tensile strain, but it wouldn't be enough just to write those down because they're just already on your formula sheet. You have to state what they mean like that. I identify a property of material A. Well, I already remembered that it was glass, using evidence from the graph to support your choice. So there's two that you can put here. The one I'm going to do is about the stiffness. It has high stiffness. So, or high Young's modulus. And I can tell that because the graph is very steep. The steepness of the graph on here tells me about the Young's modulus. So, because the graph is very steep, and the steepness, or the gradient, equals the Young's modulus. The second thing that you could have said there was that the material is brittle, because here it fractures, it extends, and then it doesn't stretch at all. It just goes crack and breaks at that point there. It doesn't go through any of this deformation here, like this copper one does. A cylindrical specimen of material A has a test diameter of 1.5 times 10 to the minus 4 meters and a breaking stress of 1.3 gigapascal. Calculate the tensile force acting on the specimen at its breaking point. So this is quite an easy question. Stress is equal to force divided by area. So the force is equal to the stress times by the area. So we just need to put the numbers in here. The stress is 1.3 gigapascals, so that's 1.3 times 10 to the 9 for giga. And then we need the area. We're given a diameter, so we just need to think area is equal to pi r squared for a circle. So r is the diameter divided by 2 squared. So we just need to do pi times by the diameter, which was 1.5 times 10 to the minus 4 divided by 2, and we need to square that. Okay, let's put that in our calculator. We'll start at this side, start with the bit that you have to square. So 1.5 times 10 to the minus 4 divided by 2, so that's the radius, square it, so we've worked out that bit now, times by pi, we've worked out that bit, times by 1.3 times 10 to the minus 10 to the plus 9 gives us the whole lot. Put it in proper units and we get 2.9728 dot dot dot. So that is going to be 23 newtons to 2SF, because everything's to 2SF here. Okay, question 3.4. Discuss which of the four materials shown in the graph is most suitable for each of the following applications. Cables supporting a lift and a bungee jump. Right, so the cable supporting the lift is going to be B, which is steel, and the bungee jump is going to be D, which is an elastic cord. Right, so to answer a question like this is one of the 6 marker questions. There'll be one of these on every single paper. To answer a question like this, what you need to do is not just say why the one that you're picking is good, but also say a reason why you might reject each of the others. So let's work our way through it. So the lift cable first, which is, we're going to pick B, which is the steel, like that. So we would, B is a strong material with a high UTS. So we pick B, look, it's the highest up here before it actually breaks. It's got the highest ultimate tensile stress. So just a little bit higher than the copper there, a lot higher than A and D. So that makes it a strong material, which is good for lifting things in buildings. And it has a high Young's modulus, it's capital Y I suppose, he's a person, Young's modulus, has a high Young's modulus, so will not stretch much under load. You don't really want the cable to stretch very much as people get in and out of the lift. Okay, it will stretch a little bit. That stretch there is elastic, that bit there will be plastic, and then it'll eventually snap at that point there. So we've said why B is good. Let's do a little bit about why A, C and D are no good. So A is no good because it is brittle. So would snap. Okay, that would be very bad for the cable under a certain amount of stress to just snap off. It also is quite weak because look, its ultimate tensile stress is quite low. It is also weak. Right, let's talk about C now. So C is actually a reasonable material to pick. It's not as good as steel, but it would be the next one that you would pick. Disadvantages of copper in real life are it's very expensive. And we've got this bit here, which is this big plastic deformation where the cable will stretch. And when it does so, the cable will permanently be made weaker. It's not a good thing to do that to a cable. So C might undergo a large plastic deformation if the load is too great. What else? It's not as stiff as B. And what else? It's slightly weaker as well, because look, it's almost as strong, but it's slightly weaker and is weaker than B. Okay, so those are the initial reasons. We've done C, now we need to talk briefly about D. So D, why might we not want D? D is too stretchy. What do I mean by that? It means it undergoes a large elastic deformation. It would undergo a large elastic deformation let's change that, with small changes in force or stress, with small changes in stress. So small changes in stress there mean that it changes its strain a lot, so it changes its size a lot. So that would mean that if you got onto the lift, it would bounce up and down, which wouldn't particularly be very good. And it's also very weak. It's also the weakest of the four. Okay, so what we've said then is we've said a good reason for B, and we've said some reasons why we reject A, C, and D. Let's do the bungee cable now. Bungee cord, we would pick D, which is the elastic. Why would we pick D? Well, when you are falling, there you are, there's your bungee rope. When you're falling down like this, when you start slowing down, you want the rope that's slowing you down to have a small tension in that rope. You want a small tension in that rope, otherwise you're going to break bones and things. If you can just imagine jumping off with a steel cable, the steel cable will go taut and it'll stop you like that, and your leg will break. But you want it to be able to stretch and slow you down over a long period of time. So that's what this is doing here. It's stretching and slowing you down over a long period of time. Remember, the steepness of this is the stiffness, so it's not very stiff at all. So D is elastic, and a small force will cause a large change in the strain. Okay, so large change in strain, small force, i.e. lots of extension of the cord. This gives the rope the opportunity to absorb all of the energy. Now you can tell the energy from a curve like this because it's the energy stored in whatever it is the area underneath the curve. So it can store lots of energy at low stresses but high strains. So in other words, it's storing the energy not by having a big force but by stretching a long way. That's how it's storing the energy. So this is good. So, and low forces, low stress, force means less harm to the person. Okay, right, now we need a little bit to reject the other three. Well, A is brittle, so you wouldn't want anything. A would not be used. As it is brittle. Okay, that seems like a really dumb idea to jump off with something that's going to snap because it's brittle attached to your leg. A, B, and C are all too stiff so the forces to stretch them are very large, meaning this is likely to cause injury. Okay, so why is that? Well, you've got to slow the person down, essentially, and these things would be incredibly strong, so incredibly stiff, which means that they would slow someone down very, very quickly over an incredibly short distance, which means that you've got an incredibly large force. You get up to a very large force over a very tiny distance. So as the person is falling down, suddenly they would have an enormous force stopping them, which might dislocate their leg or worse. All three of those would do the same, whereas this one, it has a much smaller force and stretches over a long period of time. Okay, now you could possibly go in to say that this one might plastically deform, which is not really what you want, because you might hit your head on the bottom of the canyon if it plastically deformed. But I think we've probably got enough there. We've got a good reason why we would pick each one, and we've got a good reason why we would reject the other ones. So I think that's probably a good enough answer to pick up most of the marks there. I would say 5 or 6 marks out of the 6 for that one. Okay, thank you.